and going into oxidation numbers and how you do that. And then we'll be going to into alcohol oxidation reactions and the different types of oxidants. Again, feel free to ask any questions you may have through the chat or just say it out loud. Feel free to stop me if I write something you don't understand. Let me know. I will rewrite it. So we're going to start with oxidation and reduction. You guys might remember this from Gen Chem, right? Oxidation and reduction. So essentially, oxidation is the loss of electrons, right? So when we're talking about reactions, we're comparing reactants versus the products. So if something from the reactants, right, a molecule loses electrons when it reacts, and then there's a product, right, then that is oxidation. So oxidation is loss of electrons, and then reduction is gain of electrons, so the opposite. And there's a mnemonic, right, oil rig. Some of you might have heard this. There's other types of mnemonics, and you guys can use whichever one you want. I just wrote one here. So oil means oxidation is loss, and rig means reduction is gain. And again, you guys can use whichever mnemonic you have. I also know there's one called Veoger or something like that, so you guys can use whichever one you want. So again, we're talking about oxidation and reduction in terms of reactions. So one species might be reduced or one might be oxidized when something reacts. And the fastest way to determine whether something was oxidized or something was reduced was to use oxidation numbers for the reactants and the products. So what is an oxidation number? So you guys also might be familiar with this. But an oxidation number is essentially just a hypothetical charge that an atom would have if all the bonds that it has would be 100% ionic. So for instance, draw a hypothetical bond right here, CF. So if this bond, let's say, were 100% ionic, considering electronegativity, then we would assume that that bond, those electrons in the bond, would go to F because F is more electronegative. So then hypothetically, right, this hypothetical, F would have a minus charge and C would have a plus charge because F took those electrons from that bond, right? So again, this is hypothetical. So in this case, we would assign carbon a plus one oxidation number and the F a minus one. And we'll talk more about the different situations with the whole molecule. In this example that I have right here, this reaction, you guys may notice that I have red arrows pointing to certain carbons. The reasons why I'm bringing attention to those carbons is that when we're talking about oxidation numbers, we're going to be focusing on atoms that are reacting, more specifically carbons that are reacting. So in this reaction right here, this two carbons right here have a double bond, but that double bond is replaced as two H's are added to those carbons. So we're going to be focusing on those two carbons in this reactant, and I wrote the oxidation number for those because we would focus on those when we're doing oxidation numbers, because again, those are reacting. We're breaking, so essentially we're replacing a C-C bond, right, with a CH bond. So the oxidation number might change. So you can see that it actually did change, right? So here has a -1, over here has a -2, and I'll show you how to calculate that number in a minute. And just so we can go a little bit deeper, we're focusing on those and we're ignoring the other ones, right? This carbon right here is also carbon, but we're not really gonna focus on the oxidation number for that one because it did not react. So it's attached to the same things. So we would compare, if we would compare this oxidation number that it has in the reactants versus the products, it would be the same, nothing changed, because it still has the same things attached. So it really wouldn't help us to figure out whether the reaction was oxidized or reduced because nothing is changing. So we're just focusing on what is actually reacting, what is actually changing. Any questions so far? So now we're gonna go into assigning oxidation numbers. So step one, we will assign oxidation number to each carbon that changes. Again, we're focusing on what's changing from reactant to product. In this example, I only have one molecule. It's not a reaction, so I'm gonna specify that we're working with this carbon right here in the middle. As we go through these different situations, we're just gonna focus on what's attached to that carbon. So for this first situation right here at the top, the situation is when a carbon is attached or bonded to a less electronegative atom, or when it has a negative charge. In either of those situations, if carbon is attached to a less electronegative atom or has a negative charge, we'll assign a -1. So when we're looking at this example molecule right here, there's only one bond that carbon has that is attached to a less electronegative atom. So in this case, it would be this bond between the C and the H. Circle that right there. So let's focus on this bond first, right? And let's kind of see why we're assigning a -1 to that carbon. So again, oxidation numbers is a hypothetical charge, such as if this bond was 100% ionic. So we're going to be looking at the electronegativity. So carbon is more electronegative than hydrogen. So we would assume that if this were 100% ionic, or this bond was 100% ionic, then the carbon would take those electrons, right? And it would gain a negative charge, and hydrogen would gain a positive charge, which is why we're giving carbon, so this carbon, we're giving that carbon oxidation number of -1. And this hydrogen would have oxidation number of +1. Okay, because we're looking at the hypothetical charge. So I'm gonna write this here at the bottom, because at the end, all of these numbers are gonna be useful. So carbon, we've assigned it -1, hydrogen +1. So let's move on to the second situation. This one right here. Second situation is when a carbon is attached to another carbon atom. Or if you want to think about it in electronegativity, carbon is attached to something that has the same electronegativity. Or if it's attached to an unpaired electron. If it's either the situation, we're assigning a 0. So then in this example in the bottom right here, we have a carbon-carbon bond right here. So let me draw this over here. So again, if this were, right, if we were to think that this were 100% ionic, then these two have the same electronegativity. Like they want the electrons the same, as much as the same, right? So if we would think of this 100% ionic, then one of them doesn't want it more than the other. So none of them will really have a charge. So that's why we end up saying that both of them have an oxidation number of 0. So I'm going to go ahead and write it over here. It's going to become a little bit messy. So a 0. And then the last situation is when a carbon is attached to a more electronegative atom, or when it has a positive charge on the carbon, and when those two are the situation, we'll assign that carbon a +1. So in this example at the bottom, this one right here, C double bonded to O, electronegative carbon. So to go and do this one, let's first do the example of C single bonded to O, right? Because it's going to be the same, but just ×2 for this one right here. So carbon is less electronegative than oxygen. So we would think of this bond as 100% ionic. Oxygen would take those electrons, right, and become negative, and carbon would become positive, which is why this carbon, we would give it a +1, right? So again, this is the situation, we're giving it a +1, and then oxygen would have a -1. So to do the double bond example one, it would just be ×2, right? Because it has two of those same bonds. So carbon over here would have +2, and then oxygen would have a -2. Is there any questions so far? Okay, so then let's draw it or write it over here at the bottom. It's messy, but I promise you, um, I'll explain if anyone's confused. So let me highlight the important numbers here, because again, we're only focusing on carbon. So the numbers that we wrote on carbon were 0, and that 0 was from this bond right here. And then we have a +2, and that's from this bond right here, +2, because right here. And then we also have a -1 that came from right here. Okay, so then at the end, what we're gonna do is we're gonna add all those numbers to get just 1 in total. So we have first, we have a -1 plus a 0 plus +2 with the overall charge of a +1 charge. So the oxidation number for that carbon at the end would be a +1 when we take into account all of the bonds. We have added everything. At the end, it's just going to have a plus oxidation number. Does anyone have any questions so far? So the first step, again, is just taking into account all the bonds to that one carbon for the reactants and the products. Any questions so far? Feel free to ask in the chat as well if you have any questions. Everything makes sense? I'm going to take that as a yes. Okay. So then the second step is determining the oxidation number of reactants and products by adding all of the oxidation numbers of all the carbons in that molecule. So in this example, we only have 1 carbon, but there's examples where you have 2 carbons. One example real quick. And this is the example you just saw a moment ago. Right here, we're only adding 2 H's. So we're focusing on these 2 carbons, right? Because those are the ones that are changing. But in this case, there's 2 carbons, right? So in the first step, we would have assigned these carbons a number. And in this step, we would add those numbers. Okay. But in the example that we've been doing, there's only 1 carbon. So in the second step, we would just make sure to that both of the reactants and the products have the carbon oxidation number on the carbon. But yeah, this is just, if there's 2 carbons, make sure to add them in this step, the oxidation numbers. Is there any questions for this one? Okay. So in this question, we did this first molecule right here, but we didn't do the product. So let's go ahead and do the product together as well, just so we have that, because in this next slide, you'll see them labeled. So again, this is the one we did together, but I'll do it here with you real quick again. So we have the CH bond, right? C is more electronegative. C would receive the electrons. That would have a -1. And then there's C double bonded to O. O is more electronegative. O would receive those bonds. There's 2 bonds, so we also have to take that into account. So there's going to be a +2 number there as well. And then we have a CC bond, which is just 0 right there. And then overall, we would have a +1 oxidation number for this molecule, right? Because -1 plus 2. So that would be +1. Does that make sense to everyone? Is there any questions? Okay, cool. So let's do the products together. Again, second step, make sure you have all of the carbons labeled with the oxidation number. Let's do this first. Let's do the oxygen and carbon bond, right? So oxygen is more electronegative. It would, if this were a 100% ionic bond, it would take those electrons, it would receive a negative charge, carbon would receive a positive charge. So in this case, we would label that a +1. We have 2 carbon to hydrogen bonds here. Carbon is more electronegative than hydrogen. It would receive those electrons if this were 100% ionic. So we would label this as +1, right? But there's 2 of those bonds, so I'm just going to write minus 2 plus. So it's more electronegative. It will receive those electrons. If it were 100% ionic, it would receive a negative charge. So there's 2 bonds, -2. Hopefully I didn't confuse anyone. And then there's a carbon-carbon bond. So both of them have the same electronegativity, and none of them want the electrons more than the other. So it would just be 0 and 0, right? So for this case, we have a 0, we have a +1, we have a -1, -2. So this would be -1 over oxidation for that carbon, right? So we're focusing on the carbon. So in this case, I just want to bring attention to how this changed, because again, we're focusing on how the oxidation number changed from reactants to products. And notice how it went from a +1 to a -1, right? And it became more negative. So we kind of know that reduction is gain of electrons. If you gain electrons, you become more negative. So you could start thinking of how we would be naming how reactions reduced or oxidized. We'll talk about that more on the next slide. But if it became more negative, right, as compared to the reactants, then we could think of, oh, maybe this is gaining electrons, becoming more negative, so it's reduced. But we'll talk about a more formal way to do it in step 3. So in order to decide whether something has oxidized or reduced, or maybe neither, right, we would use this equation right here. So essentially we just subtract the oxidation number from the products minus the oxidation number from the reactants. So using the example we have, right, this is our reactants right here, this is our products. So we do that, right? So -1 is the oxidation number from the products, minus +1, which is the oxidation number of the reactants, +1. So overall, we would have a -2. So that's a negative number. So then if there is a negative number that you get, then that's going to be reduction. So this is reduction. If you end up getting a positive number, that is going to be oxidation. So positive number is oxidation. Negative number is reduction. If you end up with a problem where you have 1 minus 1 and you get 0, it's going to be neither oxidation or reduction. So this problem right here is reduction. And again, I kind of said, like, if you just take a look at it, +1, this carbon is +1 in the reactants, this carbon is -1 in the products. It is more negative, right? Minus is more negative than plus. So then you can kind of see that without using this equation that it's gaining electrons, it's becoming more negative. So it's reduction, right? Reduction is gain of electrons. Also, there's another way to figure out whether this reaction is oxidation or reduction based on what bonds were replaced or what bonds were replaced and what bonds were added. So in this example, we replaced a CO bond, right? So here we only have 1 CO bond versus here where we have 2. So a CO bond was replaced by a CH bond. So here now you have, in this example right here, you have 2 CH bonds, while here you only have 1. So a CO bond was replaced by a CH bond. So let me write that down. CO bond replaced by a CH bond. So whenever you see that in any reaction, not just this one, it's going to mean there's a reduction, right? So you also have to look at what else happens. But if this is the only thing that happened, then it's going to be reduction. So that's another indication. And that should make sense, right? Because this is a C bonded to an O. In this case, O is more electronegative, so carbon would obtain a +1 charge. But in this bond right here in CH, C is more electronegative, so it would have a -1 charge or a -1 oxidation number. And so we're replacing a bond where C has a +1 oxidation number with one that has a -1 number. So it kind of makes sense that if you make more bonds more CH bonds where the C has a -1 oxidation number, then you're undergoing a reduction. Okay, someone asked a question and I'm a little confused about what you asked. Um, I don't know if you want to say it out loud. So, okay, let me try to, I'm not really sure what your question is asking. Um, but it was, so like here, we don't know you guys don't know the mechanism yet, so I'm not explaining that, but um, you just see that this CO bond here is now a single bond here, and we have created a CH bond. So you kind of like broke the CO bond and now have added a CH bond. Hopefully that answers your question. Now you could ask me again after lecture. Does anyone have any more questions? You guys are good? Okay, so this is how you would assign oxidation numbers and kind of decide whether this reaction underwent oxidation, reduction, or neither, right? And you could use the kind of intuitively look at the numbers, or you could use this calculation, or you can also just look at what bonds were broken, what bonds were formed as well. Yeah. Let's do some practice for oxidation numbers. These are just uh, molecules, so there's no reactions. So I'm going to highlight which carbons we're focusing on. So in this one, we're focusing on this one. Let me do that real quick. So let's do question 1. Does anyone want to try out question 1 and tell me what the oxidation number for that carbon is? You can also send it in the chat if you feel more comfortable with that. You can say it out loud.
-4?
Yeah, it would be -4. Do you want to explain why it's -4?
Because hydrogen is less electronegative than carbon, and it's 4 bonds to hydrogen. So each one of these bonds would assign a -1.
Yeah, exactly. That's perfect. So this one would be a -4. Is there any questions for question number 1? Okay, cool. So now let's try question number 2. Does someone want to try out this question? If you have any questions, also feel free to ask.
Be
So
-1?
yeah, it would be -1. Thank you. Yeah. So we have 2 CH bonds, right? So CH bond would give you, so it would give a -1 to the carbon. So we have 2 of them. So it would be -2. Let me just write that on the side. And we have a CO bond that gives the carbon a +1. So we just write that. And we also have a CC bond, right? So that gives a 0 to the carbon. So it's just +0. So overall, it's -1. Does anyone have any questions on that? Okay, so let's do more practice. Again, feel free to put it in the chat if you're not comfortable saying out loud. Ask me questions if you're confused. Let's do question number 3. So this is a little bit more tricky, right? It has more things going on. Does anyone want to try this out? Okay, I'm seeing questions on the chat, so let's work this out together. and see if you guys are correct. So we have 3 CO bonds, right? So we know the CO bond gives the carbon a plus charge because O is more electronegative. So overall we have +3. We also have a CH bond that gives the C -1. So -1. So +2. So a lot of you were answering +2. So you guys are correct. You guys are getting this. Let's do a little bit more practice. So let's do number 4. What do you guys think number 4 is? Again, feel free to say it out loud, chat, whatever you guys feel more comfortable. Yeah, so one of you said +2. So let's check that out. So again, we have, now we're talking about a CN bond. So this is a little bit different, but again, we're still looking at electronegativity, right? So we have 3 CN bonds. We know that N is more electronegative than C. So C, we still have a +1 charge. We have 3 of those, so +3. And then we will also take into account the CH bond, which will give the carbon a -1. +2. So whoever said +2, good job. It is indeed +2. Does anyone have any questions on this question? Make sense? Okay. So let's do question number 5. I think you guys are getting this. So what do you guys think question number 5? Yeah, +4. You guys are correct. So it would be +4 because it has 4 bonds to oxygen. We know oxygen is more electronegative. So carbon +4. Great. Hopefully you guys can see that. If not, I'm sorry, just know I did write a +4 at the bottom. So the next question, number 6, our last question. Does anyone want to give it a try? Yeah, +4. So it has 4 CO bonds. CO is more electronegative, so C will have a positive, right? There's 4 of that, so it's going to be +4. Okay, great. Any questions on that? Or anything I just went over? Okay, so I did write the numbers on the next slide so you guys can have them for practice. Last, I just kind of want to do a little bit of review of what I said about like breaking bonds and like forming bonds. So I just want to show you guys a trend on this, just to kind of reiterate what I said. So notice as you go to the right, there's increased reduction. But notice, okay, so first I highlighted the carbon to oxygen bonds yellow and the carbon to hydrogen bonds blue. So this be hydrogen, this be hydrogen. Notice as how you get more CH bonds, the reduction changes. So again, you're replacing a CO bond with a CH in this case. So for instance, as you go from here to over here, that bond was replaced by a CH, and that's increased reduction. So if you ever have, like, for instance, if we focus on these two, some reaction occurred that created from this reactant, this product, right? There was only this change in this carbon where this carbon went from being bonded from a CO, it went to being bonded to a CH, then you kind of can tell that there was a reduction in the molecule, right? So again, reduction is gain in electrons. So that's a way to do it. And it's kind of just the opposite for oxidation. So if we look at the reaction being the other way around, where a CH bond was replaced by a CO bond, right? So this one right here would be replaced by this one, then it would be oxidation. So it would just kind of be the opposite. Does anyone have any questions? Did that make sense to everyone? If it doesn't make sense, just look at the slide and kind of figure out what is happening and what is changing. But this is kind of a trend that might help you figure out whether a reaction is being reduced or oxidized. But yeah, any last questions? Not, I will move it or send it over to Cindy.
Hi, everybody. Thank you, Ashley. Let's go ahead and talk a little bit about classifying alcohols before we move on to some alcohol oxidation reactions. So just to review the definition of an alcohol, it's an alcohol in which one of the hydrogen atoms in an alkane have been replaced by an OH group. So this is just an example of what an alcohol could look like. I drew the specific alcohol in blue, but it's an OH group connected to a carbon. Basically, that's an alcohol. And just as we classify carbocations as primary, secondary, etc., we can classify alcohols as primary, secondary, and tertiary. So to do that, you're going to look at the carbon that the alcohol is attached to, and you're going to think about how many other alkyl groups that carbon is attached to. In the examples in this lecture, I've used methyl groups for the alkyl, but just keep in mind, like literally any other group, alkyl group could be substituted here. This is a primary alcohol. The carbon that the alcohol is on is attached to one other alkyl group. And note that methanol is also considered a primary alcohol, even though like this carbon that the alcohol is on, it doesn't have any other carbons attached to it, but it's still considered a primary alcohol, just to make everybody aware. And then a secondary alcohol, the carbon that the alcohol is on is connected to two other alkyl groups. And tertiary alcohols, if you can guess the pattern, the carbon that the alcohol is on is connected to three other alkyl groups. So I was hoping that we could do a couple of practice problems to classify these guys. Let's start with the one on the far left. Yes, that is the left. What type of alcohol is this phenol? So I actually went ahead and highlighted the carbons that this sort of central carbon that the alcohol is on is connected to. Because this carbon is connected to two other carbons, the ones that are highlighted, this is a secondary alcohol. How about this next alcohol? And you can feel free to speak out loud or paste it in the chat. Sometimes it's kind of hard to monitor both. So just like in the past example, this carbon right here that our alcohol is on, this carbon is connected to two other carbons or alkyl groups. So this is also a secondary alcohol. Alrighty, how about this alcohol right here? Somebody said tertiary, perfect, you guys are pros. As you can see here, there are three different alkyl groups highlighted. This is the carbon that our alcohol is on. This is going to be a tertiary alcohol. And then lastly, let's look at this alcohol right here. Primary, somebody said primary. Thank you so much for answering. Yep, this is a primary alcohol. This is the carbon that we want to look at because it is connected to our alcohol group right here. This carbon is connected to 2 hydrogens that are not shown and 1 other alkyl group. So this is a primary alcohol. Are there any questions on classifying alcohols? Alrighty then, let's move on. We're going to discuss some functional groups that we haven't really talked about too much during OCSP this summer. This is an aldehyde. As you can see, we have our carbon connected to a double bond. Carbon connected to oxygen via a double bond. This is called a carbonyl group. And we have our other alkyl, which is represented by this R, which stands for rest of molecule. And then we have an H right here. And this type of a functional group is called an aldehyde. Next, we have a very similar looking molecule. The only difference is that instead of a hydrogen, we have an alcohol right here connected to the central carbon. This is a carboxylic acid. You've probably heard the term before, but for our reactions with alcohols, it's good to know what it looks like. And then lastly, we have a ketone. This group is different from the other groups because instead of a hydrogen or an alcohol, we just have another alkyl group. So basically, yeah, this is a ketone. And this page will be handy to reference as we go through some of our reactions with primary, secondary, and tertiary alcohols. Alrighty. So our first reaction with a primary alcohol is going to be an oxidation. We're going to write a list of some of the most common oxidizing reagents. And they are, hang on a second, they are Kr2Cr2O7, Na2Cr2O7, CrO3, and H2Cr04. All of these have a species of chromium-6, and they are all considered strong oxidants. So basically, they can all do pretty much the same job since they have the same chromium species. Another strong reagent that can also be a strong oxidant is KMNO4. That's another one that can, again, kind of do basically the same job as the other 4 reagents. So this is our list. And whenever these guys are running a reaction along with an acid, you can oxidize a primary alcohol all the way to a carboxylic acid. And the reason that I'm specifying that you can oxidize it all the way to a carboxylic acid is because the process of oxidation, first you would take the primary alcohol and go to an aldehyde. And the next step, like the most oxidized version, is the carboxylic acid. However, in this reaction with these reagents, you are not able to stop at the aldehyde stage. You have to go on to the carboxylic acid. So let's take a look at our reaction. Let's assume that we have some Kr2Cr2O7 and we need some acid. So let's pick a strong acid. Let's do H2SO4. And this is our primary alcohol. So again, as I mentioned, the first kind of step in oxidation is to go to an aldehyde. As you can see, this is an aldehyde because we've got our carbonyl, we've got our R group, and we've got our hydrogen. However, we can't stop here. We have to keep going, and we end up with a carboxylic acid. Now, I'm sure you guys might be wondering, what's the mechanism for this reaction? The mechanisms are going to be covered more in Chem 3580, which is second semester Orgo. So for OCSP and for the most part, 3570, you're not expected to know the mechanisms. but you are expected to be able to recognize the reagents and be able to predict the products. And knowing what reagents can produce which products will be very helpful in your synthesis type problems when you're given a starting material and you're expected to run a series of reactions to get a specific product. Are there any questions about this reaction? Alrighty, let's go ahead and move on. So this is a little bit of the background behind the reaction. I know I said we didn't need to know the mechanism, but some people might be a little bit curious about what's going on. This is basically our aldehyde. So let's assume that we've already oxidized a primary alcohol, and let's suppose we're at that spot where we're at the aldehyde. In the presence of acid or water, you are able to get to this hydrate intermediate right here. So this is a reaction that occurs with, remember, H3O plus can dissociate into H plus water. So if you have acid like our strong acid that we had earlier, basically this reaction is going to be going on in both directions. You're going to end up with your hydrate in the presence of water or acid. And then if we have some of that chromium 6, a chromium 6 reagent, or our KMNO4 reagent, but I'll just draw chromium 6 here. In this presence, we are going to move on to a carboxylic acid. So if you don't have water or acid present, you aren't going to be able to get to the carboxylic acid stage, and that's when you're going to be able to stop the reaction of a primary alcohol at an aldehyde. So these reagents that run without any water or acid present, they're known as what's called anhydrous reagents because they don't have any water. So a good example of an anhydrous oxidant that you should be familiar with is PCC, which is an abbreviation for pyridinium chlorochromate. And this is an example of what it looks like. We've got our CrO3. We have a pyridinium group. This is a functional group you'll get familiar with in Chem 3580. And we have an HCl associated with this group as well. So this is kind of what it looks like. And this is a very good anhydrous oxidizing reagent. So here we have our primary alcohol. Let's assume that we are using PCC and this solvent right here. As I mentioned earlier, this is an anhydrous reaction. We do not have any water or acid, so this reaction is going to stop at the aldehyde stage, and we are not going to be able to oxidize this primary alcohol into a carboxylic acid. This is an aldehyde, as you can tell by the hydrogen instead of the alcohol group next to the carbonyl right here. Another anhydrous reagent that can do the same type of reaction that you should also be familiar with is DMP, and it works basically the same way. Oxidizes a primary alcohol into an aldehyde. Are there any questions?
Sorry, could you re-explain why it doesn't go past the aldehyde part?
Sure. So on the other side, basically for anhydrous reactions, they do not have this acid or water. So for that reason, you aren't able to make this hydrate intermediate, and you are unable to go on to the carboxylic acid stage. You're basically stuck here. In order to go from an aldehyde to a carboxylic acid, you have to have some source of water or acid. And in this reaction right here, there's no water or anything present. So the reaction is going to go to an aldehyde. But if I were to add, suppose I threw in some water right here, that's when I think you would be able to move on to a carboxylic acid if you had some sort of chromium present, as we do here. Does that make more sense?
Okay, thank you. Yeah.
Yeah, thanks for asking a question. Are there any other questions? Okay, if there are no further questions, I'm going to go ahead and move on to talk about reactions with more alcohols, namely secondary and tertiary alcohols. So for secondary alcohols, it's a little bit easier. They are oxidized to a ketone in the presence of any oxidizing reagent. So we talked about how oxidizing reagents such as K2Cr2O7 or other chromium-6 reagents or KMnO4, those are pretty strong reagents. They can oxidize a primary alcohol all the way to a carboxylic acid, while PCC can only oxidize a primary alcohol all the way to an aldehyde. However, for secondary alcohols, it doesn't matter what type of reagent you have here, you're going to end up with a ketone. So this reaction here has PCC in it. I could replace PCC with K2Cr2O7 or literally any of the oxidizing reagents that we've talked about before, and I would still end up with the same ketone product. So definitely makes things a lot more simplistic when you are trying to come up with products on your problems and exams. If you see a secondary alcohol, you know what the product's going to look like, regardless of what type of oxidant you have. And then tertiary alcohols are even easier just because they simply cannot be oxidized under normal conditions because they lack the specific carbon to hydrogen bonds. They have to be broken in the mechanisms. Again, the specific mechanisms for an oxidation reaction of an alcohol, those are covered in Chem 3580, so you don't need to worry about them at this time. Just focus on recognizing I see a tertiary alcohol, it's not going to get oxidized. And professors love to throw questions out there. Well, they'll give you some alcohol and say, predict the product. But sometimes the answer is no product if it's a tertiary alcohol. Alrighty, so before we do some practice problems with alcohol oxidations, let's talk a little bit about the definitions for weak and strong oxidants. We can very briefly review what I've just been talking about for the past couple minutes. So weak alcohol oxidants, also known as kind of these anhydrous oxidants like PCC and DMP, they will oxidize a primary alcohol to an aldehyde only. Strong oxidants, that's anything with our CR6 combination or this KMnO4. You should learn to recognize those reagents because they will oxidize primary alcohols all the way to carboxylic acids. And then, as I just mentioned, secondary alcohols are always oxidized to ketones, regardless of oxidant strength. Are there any questions that I can answer before we start doing practice problems? Okay, I'm not seeing any questions, so let's go on and do some practice. We have this starting molecule. It's got a couple of different alcohols on it, and then we have 4 different reaction conditions, and we are asked to predict the product in each of these conditions. So before we start to thinking about what's going to happen, let's consider what type of alcohols are on this molecule. So I've highlighted 2 of the alcohols in different colors. What type of alcohol is highlighted in the tannish orange shade? Feel free to speak out. Feel free to write it in the chat. So this alcohol over here, this is a primary alcohol because as you can see for this carbon is only connected to one other alkyl group. Then what about this carbon that is highlighted in teal? I see somebody's answered in the chat. This carbon that is highlighted in the teal is actually going to be a secondary alcohol, because that's an ugly arrow. There we go. The carbon that this alcohol is on, we see that it is connected to 2 other alkyl groups. So this is a secondary alcohol. And we know that secondary alcohols are always oxidized to a ketone. So let's keep that in mind. And then lastly, we have this remaining alcohol, which is unshaded up here. Does anyone want to answer what type of alcohol this one is? So somebody answered that this was tertiary, and they are correct. Thank you. This is a tertiary alcohol, which makes our lives a whole lot easier because it doesn't actually get oxidized. So basically, the only wild card we have is with our primary alcohol over here. So we're going to need to consider each of our reaction conditions and think about whether it's going to be oxidized after all. Alrighty, so let's look at our very first set of reaction conditions. We see that we are presented with some acid as well as this KMNO4 and some NaOH. So I guess the main focus of the reaction is the KMNO4 specifically because that's a reagent that we talked about. Does anyone remember whether KMNO4 is a weak oxidant or a strong oxidant? Somebody says it's a strong oxidant. They are absolutely correct. The strong versus weak oxidant thing that only really is relevant for our primary alcohol. But let's go ahead and start drawing out our product. So because we have a strong oxidant, are we going to have an aldehyde or a carboxylic acid for our primary alcohol? Somebody says carboxylic acid, totally correct. This right here is going to be a carboxylic acid. What about for our secondary, good gracious, our secondary alcohol? We already mentioned that's always going to be oxidized to a ketone. So regardless of what type of reaction conditions we have, this alcohol is always going to look like this. And then we talked about how up top, our tertiary alcohol is just not going to get oxidized. So we would not expect this alcohol to change at all for any of these examples. Okay, how about our second set of reaction conditions? Is DMP a strong oxidant or a weak oxidant? Somebody says weak, perfect. Yep, this is a weak oxidant. It's going to oxidize without the presence of any water or acid. So we would expect our product to look basically the same with the exception of one exception. We're going to have our aldehyde instead of a carboxylic acid because this is a weak oxidant, so a primary alcohol is going to be oxidized to an aldehyde and not a carboxylic acid. Let's look at reaction condition number 3. Do we have a strong oxidant or a weak oxidant? This is going to be a strong oxidant, which means that our reaction product should look the exact same from our first example. As we mentioned, like any sort of oxidant that has either a chromium 6 species or KMNO4, they're all going to work very similarly, and they will be able to oxidize our primary alcohol all the way to a carboxylic acid. And lastly, let's consider our fourth species of, our fourth reaction set. Is this a strong oxidant or a weak oxidant? So this is going to be a strong oxidant. And again, our product is going to look very similar to the first and the third. Right, like that. Excellent. Alrighty. So this is a good type of example of the sort of work that you're going to have to do. Like a lot of practice problems will have more than one alcohol. So you should be sure for your first step, consider what type of alcohols are present in the starting material, and think about what type of reaction conditions you're given each time. We only have like a couple minutes left, so I'm going to work through our last page of practice problems very quickly. For this first example, this is a weak oxidant, as I'm sure you probably know by now. So the product is going to feature our primary alcohol, since this is a primary alcohol. It's going to feature an aldehyde. So we're going to have a hydrogen hanging off instead of an alcohol group, no carboxylic acid. Right here, I'm sure you'll recognize CrO3. That is a strong oxidant. So this again is a primary alcohol. So we're going to have, in this case, basically the same thing, only it's going to be a carboxylic acid. And then lastly, as we had previously, we have PCC here with our CH2Cl2 solvent that you're going to be seeing a lot with anhydrous reactions. This is a weak oxidant. And then if we look quickly at our alcohols, we can see that we have one primary alcohol, since this carbon is only connected to one other carbon. And then we have two secondary alcohols. And we also have a tertiary alcohol. So we really got everybody here. And our product is going to look a little bit like this. We've got our tertiary alcohol, which totally did not change at all, since tertiary alcohols are not oxidized. We have our primary alcohol converted into an aldehyde. And then we have our two secondary alcohols converted into ketones, because secondary alcohols are always converted into ketones. Alrighty, so this is all that we have for you for today. I highly recommend, if you have time or if you need extra practice, you can go through and work on these practice problems on your own, since they'll be posted online as usual. And yeah, I'm happy to stay behind if anybody has any questions, but otherwise you are free to go.
Thank you. Have a good weekend.
You too. Have a
too.
good weekend. Sydney, I think we're good.
Okay, great.
Alrighty, I'm gonna close the meeting.
Great. if you want, do you want me to post the slides again? If you want to go ahead and share them again, I don't know if you made any changes from yesterday. I
Yeah,
can go
I'll
ahead and get,
yeah, right now.
oh, okay, I can post them.